Hi friends, welcome back to my channel. Still on Power Machines N5. Today we are doing a calorific value of a fuel. My name is Tsepo. Please subscribe to my channel to make sure you keep on receiving videos like this. Click that notification button so that you will be notified every time I post a new video. So calorific value, CV. Calorific value is the amount of heat released by a fuel during the complete combustion of that fuel. This chapter is a continuation from our previous chapter, which was combustion of fuel. So by now I hope you know what combustion is. I'm not going to explain that again. And then the formula is given by ME plus MW times specific heat capacity of water times the temperature difference, all by the mass of fuel. So we know that let's say we have a container of water, and then we have the combustion chamber here. This is where we are burning the fuel. So the only way to know the amount of heat that is being released by the fuel that we are burning here, one example is to put water, and then the water will receive the heat energy from the coal, and then at the end we can be able to calculate the amount of heat that was produced by the fuel. So this is the formula to calculate our calorific value, which is the calorific value times the mass of the coal, and then time is equals to the heat energy that will be received by the water. So remember boiler efficiency. We know that there is no such a thing as 100% efficiency. So not every heat energy that will be produced by the coal will be transferred to the water. So, but in this case, we will only be looking at the losses that take place because of the molecule H, which is hydrogen. We know that every time a hydrogen undergoes combustion, it will form a product which is water, and then this water is in the combustion chamber. So some of the energy that is produced by the fuel that we are burning will be used to convert this water into steam, and then the steam will leave the combustion chamber with some of the energy that is being produced by the fuel. So in the total amount of heat that will be produced here, we will minus the amount of heat that left with the steam. So we will have now another formula that says it's a low calorific value, and then the low calorific value. Because this is a low calorific value, we will say this is a high calorific value. The low calorific value will say it's equals to the high calorific value, which is the total amount of heat that is produced by the coal or whatever fuel that we are using, minus the heat energy that left with the steam due to the presence of hydrogen in the combustion chamber. And then the formula goes like this. It's 9H2, which is the amount of hydrogen that is in the system, times the latent heat of the water. Yeah, so that's everything that we need on this topic. So we are good to go. and attempt a question. See how do we apply this information. So with me, I have a question that's from the question, the textbook. We will do and then see how do we apply this information. So the question reads as follows. A bomb calorimeter was used to determine the higher calorific value of a sample of coal, and the following results were recorded. Mass of coal, they say, is 0.915 gram. Mass of water in calorimeter, it's equals to 2,250 grams. And then water equivalent of calorimeter, it's equals to 420 grams. And then they said the initial temperature of the water in calorimeter is equals to 31 degrees Celsius. The final temperature of water is equals to, in the calorimeter, it's equals to 32.7. And then they say calculate the higher and lower calorific values in megajoules per kg, assuming the coal has a hydrogen content by mass of 16% at a room temperature. Latent heat of steam is equals to 2.453 megajoules per kg. So we have our data. They gave us the mass of the fuel, mass of water, the mass of the equivalent water, and then equivalent water. And then we have the initial temperature and the final temperature, the amount of hydrogen in the system or in the coal, and then we have the latent heat, latent enthalpy, and then we know they are looking for the high calorific value, which is given by HCV. It's equals to the ME plus MW times specific heat capacity of water times the temperature difference divided by MF. We know that the specific heat capacity of water, specific heat capacity of water is given by 4.187 kilojoules per kg Kelvin. But they said they want our answer must be in megajoules. So we substitute our ME. That's 2. It's 2 plus our M of water, mass of water is 250. Then our specific heat capacity. Our specific heat capacity is 4.187. And then to make things easier, we can convert this to megajoules so that there will be no need for us to convert after calculating and after this stage. So we will convert the specific heat capacity from kilojoules to megajoules. And then the change in temperature, our change in temperature is this minus this, which is 32.7 minus 31 degrees Celsius, divided by the mass of the fuel. Our mass of fuel, where is mass of fuel? This is our mass of fuel, which is 0.915. And then we get our answer, which I got 20.77 megajoules per kg. So it is very important that your mass, the mass of water, the mass of fuel, and the mass of the equivalent water are in the same unit. So we got our answer as 20.77 megajoules per kg. And then another thing, they said we must calculate the lower calorific value. calorific value. So we know that the lower calorific value is equals to the higher calorific value, which is this one, minus 9H2. Yeah, it's 9H2. Yeah, 9H2 times HFG. So we are calculating for the lower calorific value per kg. That tells us that we are dealing with a mass of 1 kg. And then they said in the system we have 16% of hydrogen, which give us a mass of the hydrogen as 0.16 kg, because we are dealing with 1 kg. So we can come and say our high calorific value is 20.77 minus 9 times 0.16, which is this mass, times the HFG they gave us, and then it is already in megajoules, so there is no need for us to convert. And then it's 2.453, and then I got my answer as 17.238 megajoules per kg. So it is that simple. We are done with the question. They said we must calculate for the lower calorific value and the higher calorific value. So yeah, that's the end of it. So this was like a foundation. Let's build up on it. I have another question paper, or another question. This is a question from a question paper which was written on let me check 29 November 2019, and then the question reads as follows: the composite of a sample of fuel according to mass is 85% of carbon, 7% of hydrogen, 6% of sulfur, 2% of oxygen. And then the calorific values are as follows. Carbon, it's 34 megajoules per kg. Hydrogen is 142 megajoules per kg. And then sulfur is 9 megajoules per kg. And then they gave us the vapor pressure, which is 5 kilopascal. And then the questions, they say calculate the higher heat value of the fuel in megajoules per kg. So they gave us our information. They gave us the analysis of the molecules that are in the fuel. And then they gave us their calorific values. So remember, in the previous question we were calculating the calorific, we dealt with the calorific value of the fuel as a whole, but now they gave us the calorific values of each and every molecule that is found in the fuel separately. And then now, using this analysis, we must get the total amount of calorific value of the fuel. And then the calorific value of the fuel, because now we are dealing with mass 1 kg, we know that 85% will be 0.85, and then 0.07, 0.0 0.02, and then this will give us 1 kg. And then the first question, they said we must calculate for the high calorific value, and then we will say the high calorific value will be, let's start with carbon. The calorific value of carbon 34 34. But this 34 megajoules is for 1 kg of carbon. But since in the system we only have 0.85, we will times the 34 by 0.85, and then this will give us the total amount of calorific value of the carbon in the system. And then we go to sulfur, and the calorific value of sulfur, it's 9 megajoules, which will be 9 times the mass of the sulfur in the system, which is 0.06. And then this will give us the total calorific value of sulfur in the coal. And then we go to hydrogen. It's plus, sorry. So since we have oxygen in the system, when we have oxygen in the system, we assume that the oxygen that we have in the system will combine with the 0.02 kg of oxygen in the system will combine with a certain amount of the hydrogen in the system. And then that portion of the hydrogen that has already undergone combustion with the oxygen that is already in the system, we will have to calculate for it and then minus it in the total amount of hydrogen in the system, so that we do not include it here when we are calculating for the high calorific value or the total calorific value of the fuel. I repeat, if we have oxygen in the system, we assume that the oxygen that we have in the system, by the time we start combustion, we will say that the oxygen that is already in the system has already undergone combustion with some of the hydrogen that is in the system. And then our job, before we can calculate for the total calorific value of the hydrogen in the system, we will have to find the amount or the mass of carbon or of hydrogen that has already been used by the oxygen that is in the system, and then calculate for it, minus it from this mass of the hydrogen, and then we will neglect that mass of hydrogen. So how do we calculate for the mass of hydrogen that has already been used by the oxygen? We will say that the total amount of hydrogen, which is 7, let me just write it, 7.07 minus the amount of oxygen, which is 0.02, divided by 8. We know where does this 8 comes from. We know that for hydrogen plus, it's going to give us H2O, and then it's going to be 189. So this is the 8 that we divide by here, and then we will get the amount of hydrogen that we will use in calculating for our high calorific value of the fuel. And then let me just write it like this. The calorific value of hydrogen is 142 times, let me say, this 0.06 minus 0.02 divided by 8, and then we get our high calorific value. And then I got my high calorific value as 39.025 megajoules per kg of the fuel. So the formula for this, yeah, it's important that you write the formula. it will be the calorific value of carbon times the mass of carbon, the calorific value of sulfur, times sulfur, and then it will be plus the calorific value of hydrogen times, and then we do this, the mass of hydrogen minus the mass of oxygen divided by 8. So this is the formula. It's important that you write the formula first before you come to the substitution. And then our 6.2, they said we must calculate for the lower heat value of the fuel. We already know how to calculate this. LCV, it's equals to high calorific value minus 9H2, if I'm not mistaken, and I'm not, times HFG. So our high calorific value, we will be using this one, 39.025 minus 9, minus, and then the value of the hydrogen in the system is 7%. This is it, 0.07 times the HFG. We will use the pressure that they gave us. They said it's the pressure, they said it's the vapor pressure. And then with when we have this, we go to the steam table and then extract the value of HFG, which I got as, so the value will be 2424 kilojoules per kg, but we already have our high calorific value in megajoules, so we will have to convert this as well to megajoules, and then we will say is 2.2, which will give us 2.424 megajoules, and then we calculate, and then I got my value for LCV as 37.498 megajoules per kg. Yeah, this is number one. Number two, and then number three, they say if some of the fuel heat is further absorbed by the dry fluid, if some of the fuel heat is further absorbed by the dry fuel exhaust gases, calculate the available heat value AHV of the fuel in megajoules per kg. And then they say air temperature is 36 degrees Celsius and dry exhaust gas temperature is 230 degrees. Take specific heat capacity for exhaust gases as 1.045 kilojoules per kg. So now in this question they are saying if from this calorific value, if some of the heat energy is further absorbed by the dry exhaust gases, the dry exhaust gases, which will, with this being the temperature difference of the exhaust gases, what will be the available heat value if some of the heat will be absorbed from this stage, so that the rise in temperature will be from 36 to 230 degrees Celsius, and then they gave us the specific heat capacity. So first we must get So okay, this is the formula that we will use, the available heat value. The available heat value, we will say the low calorific value minus, and then we minus the heat energy that is being absorbed by the dry gases, and then we will say the mass of the exhaust product times its specific heat capacity times its change in temperature. And then we know that we will have dry products from this. We will have from carbon, we will have carbon dioxide, and then from sulfur we will have sulfur dioxide. So this carbon we do not consider it because it is not a dry it will not produce a dry product. And then we say, since we know that in combustion we will have to let air in by mass, which is 23% oxygen and then 77% nitrogen. That tells us that nitrogen will also be a part of the exhaust gases in after combustion. And then our first task is to find the masses of these three. So we know that the mass of carbon, it will be given by 3.667 times 0.85, and then I got my answer as 3.117, and this is from our previous chapter. So the sulfur dioxide is kg. Sulfur dioxide is going to be 2 times 0.06, and then our nitrogen, we will have to calculate first the amount of air in the system. And then we know that to calculate the amount of air in the system, we will say carbon first, 2.667 times the amount of carbon in the system, which is 0.85, plus the amount of sulfur to oxygen, hydrogen first, which is 8 times is, I think it's 8, yeah, 8 times 0.07 plus, okay, let me put it here, plus the amount of sulfur in the system, which will be 0.06, minus the total amount of oxygen that is already in the system, which is 0.02, and then we will get the amount of air in the system, which we will say this will give us the total amount of oxygen, but we are looking for the amount of air. Then we will say times by 100 divided by 23 to get the amount of air in the system. And then I got that the amount of air in the system is 12.465. So to get the amount of nitrogen from this air, we will say 0.77, which will give us the total amount of nitrogen as 9.598 kg. And then we will come and add it here, 9.598 kg. I didn't calculate for this. This will give us, let's say, this will give us what? Let me do this fast. This will give us 2 times 0.08. This will give us 0.12. And then we come and say the total, let me erase this, the total amount, the total mass of the product will give us 12.835 kg, which we will put here, and then we have the specific heat capacity. This is the specific heat capacity. We also have the temperature difference, and then from there we can get the value of the available heat value. We already know that our LCV is 37.498 minus our mass, which is 12.835, times our specific heat capacity, which is 1.054, times our temperature difference, which will be 230 minus 36, and then I got that my answer is 34.896 megajoules per kg. And then this is what they have asked. This is the end of our question. So this thing is not difficult. Just you need the background of the previous chapters. So if you didn't do the previous chapters, I will suggest you just go and watch those videos now before you can come and watch this, because if you didn't go through the previous chapters, this can be very confusing. So that is basically the end of our lesson today. Hope this lesson will be of help to you. My name is Tsepo. Please subscribe. Please don't forget to subscribe to my channel, like this video, share it with others, and comment. From me to you, I will see you on the next lesson.